Okay, so here we are. We're going to be studying acids and bases. This is part B of experiment 8, right? Last time, what we did was we came up with a very quick definition of what an acid or a base are, depending on the question, what happens when you put the substance in water? That is the basis for the so-called Arrhenius definition. And what we see is that when you put an acid in water, such as HCl, which is a gas, but then you put it in water, it generates hydrogen ions. If you put something like sodium hydroxide, a solid, in water, it dissociates and it produces hydroxide ions. And that's the essential definition. What happens when you put it in water? If it's an acid, it produces hydrogen ions. If it's a base, it produces hydroxide ions. And then when you combine them, you can have a reaction where, let's say, HCl plus NaOH. We saw how this is the format, the typical format of a double replacement reaction, where the H and the Na switch places. And so the sodium ends up being part of a salt solution with chloride. And the hydrogen and the hydroxide ions basically produce water. Because neither one of the products can ionize to give me any more hydrogen or hydroxide ions, we call this sometimes a neutralization reaction, right? Call this a neutralization. The Arrhenius definition is very useful because we do a lot of chemistry in aqueous solutions, in water. But here's the thing. For example, the definition does not explain always how you get these ions. I mean, from sodium hydroxide, it's obvious how you get hydroxide ions. But we know that ammonia is a base. And the question would be, how do we get hydroxide ions from ammonia? As you can see, the molecule of ammonia doesn't have any OHs in it. How do you get them? So one of the approaches that we take is the following. Instead of asking what happens to the substance in water, we can ask, what does the substance do to the water? It's kind of a way of looking at the substance, not from what happens to it, but from what it does chemically. So let's consider then that approach. Let's say that we're going to ask, what does the substance do to water? So let's consider HCl. And let's say that we already have HCl in solution, and we're not going to consider what it does to water. So we're going to bring water up as if it were a reactant. And what does happen? Well, what happens is that, again, what HCl is actually doing is it is transferring a hydrogen to the water molecule. It's leaving the chloride ion who keeps the electrons, and the other product is a polyatomic ion called the hydronium ion. And that is the real form of this so-called hydrogen here. Remember, if hydrogen is atomic number 1, that means it has proton, electron, right? If you get an H+, that means you dropped off the electron, so you're left with a proton. The Arrhenius definition, it's kind of like demanding that we have protons in solution, which is not a very stable kind of thing. Instead, this definition, which was given by Bronsted and Lowry, says that it's not that the acid produces a proton, it's that it transfers a proton to water and generates the hydronium ion. So in this definition, the acid is essentially a proton donor. Okay, now the effect is the same. This could be seen as a shortcut or maybe like a short version of this, but this is actually what is happening. The hydronium ion is for real. Okay, that is the way this so-called proton exists. It's been transferred. So this allows us to look at the question, how do we get hydroxide ions out of ammonia where it's not visually evident that you could get hydroxide ions from it? Again, here's the thing. You're not thinking what happens to ammonia. You're going to ask, what does ammonia do to water? So let's ask ourselves, when I put ammonia in water and I react it with water, what I'm going to see then is a transfer again of a proton from the water to the ammonia. And what I'm going to end up getting is an ammonium ion and guess what? If the water molecule gives off a proton of hydrogen but keeps the electrons, what you are left with is our good friend, the hydroxide ion. In other words, the hydroxide ion was not coming from the ammonia molecule. It actually came from water. And so ammonia is considered a base as a proton acceptor. So this view of acids and bases is broader because it allows me to explain exactly how those ions are being produced. Not only that, but it allows me to propose an acid-base reaction in the absence of water. So what if, what if there's no water? So I'm going to take now ammonia in its natural form as a gas and HCl in its natural form as a gas. Remember, the acid is going to donate a proton to the base, and what you get is NH4 and chloride ions. But there's no water for these guys to get dissolved. So what does a positively charged ion do when it sees a negatively charged ion? Party on, dudes, right? They're going to link up and form essentially ammonium chloride, which, as any other ionic compound is in the absence of a solvent, is going to be a solid. So that's the experiment that I showed you in lecture today, where you had the two bottles and allowed the fumes to go up and mix, and that's the product that you get. Now, this definition of an acid and a base allows you to do something interesting, and that is to consider kind of like setting up an acid or a base from the perspective of not how much material I have, but how much chemical power I have in there. For example, let's consider the reaction of HCl with NaOH. Move this over here. Get this faucet out of the way. There we go. Okay, let's get this out of here. Let's get this out of here. Let's move you out here. There we go. HCl and NaOH. So remember that, again, just like in the Arrhenius explanation, we're going to have the same products. The difference now is that the way we look at it is the acid is donating a proton to the OH minus, which is the base, and you get NaCl plus water. Now, what I'm going to consider now is not what happened to the HCl, the acid, but what did the acid do? Well, I can see stoichiometrically that 1 mole of HCl reacted with 1 mole of NaOH. In other words, neutralized 1 mole of NaOH. If I wanted to know, like, how much HCl I have in there, instead of calculating the moles per liter, I might consider what's the chemical power in my sample. And I would say that 1 mole of HCl, we would say it has 1 equivalent. In other words, 1 mole of HCl has the power of transferring 1 mole of protons to a base. 1 mole, 1 equivalent. So let's say that I have a 1 molar solution of HCl. 1 molar HCl. So that would be 1 mole of HCl in 1 liter. But I just saw that 1 mole of HCl has 1 equivalent per mole. So I can cancel that out, and I get that 1 mole per liter of HCl is 1 equivalent per liter. And this is the basis for another way of measuring concentration. This is called 1N. This would be the normality. Normality is a way of measuring the concentration of this acid, not in terms of what there is in there, but how much chemical power there is per liter. Why is that meaningful? Well, let's look at what happens with a different kind of acid. Let's consider sulfuric acid. H2SO4 reacting with NaOH. Now, in this case, my product is going to be a salt again, but this is sodium sulfate, which means I need 2 sodiums for every sulfate ion. And so because of that, I had to balance that equation over here. And that means that I'm going to have 2 hydrogens and 2 hydroxides producing 2 molecules of water. All right. So when I balance the equation, what I find in this case is that 1 mole of sulfuric acid can neutralize not 1, but 2 moles of base. Or in this new language we're proposing, we would say that 1 mole of sulfuric acid has not 1, but 2 equivalents of, let's say in this case, proton transferring power, right? It's a measure of its chemical activity not of the number of particles per liter. So if I now have a 1 molar solution of sulfuric acid, that means I would have 1 mole of sulfuric acid for every liter. But in this case, 1 mole of sulfuric acid contains 2 equivalents of chemical power. So when I cancel this out, I get 2 equivalents per liter. In other words, a 1 molar solution of sulfuric acid is 2 normal. Notice that to say that they're both 1 molar does not distinguish exactly the chemical power that's in there. To say that HCl is 1 normal and sulfuric acid 2 normal, it gives me a window into the chemical power that each one of these acids has. So it's a different way of measuring concentration from the ones that we studied in class, where it was about moles per liter, right? So it's a very interesting kind of approach here, all right? So let's go ahead and see what the object of our experiment is today. Since these reactions between acids and bases are very coordinated by the stoichiometry, and since I have a way of relating the stoichiometry of the reaction with what I had in there, if I have a solution of one of them and I want to find out what is its concentration, I can simply run a chemical reaction against another reactant for which I know the exact amount and use the stoichiometry of the reaction to calculate what is the concentration of my unknown. And this is a technique called titration, all right? So let's go back. I'm going to go over the slideshow here.
Okay, as I explained in my, somewhat blurry introduction there video, we are going to use a technique called acid-base titration, and the main instrument that we'll be employing is glassware called a Buret. So again, remember that in water, acids ionize to form hydrogen ions and bases dissociate to form hydroxide ions. So we're studying the reaction of an acid with a base where the hydrogen ion from the acid combines with the hydroxide ion from the base to make water. Now the cation from the base combines with the anion from the acid to make the salt. It's kind of like what we studied in class, a double replacement or double displacement reaction. Essentially, in this case, for example, when HCl reacts with NaOH, it's as if the hydrogen and the sodium switch places. The sodium ends up with the chloride ions to form a salt solution, and the hydrogen ion reacts with the hydroxide ion to form water. Here's a table that we've seen before, some common acids and bases. Some of these, as we have kind of discussed briefly, are what we call strong acids. In other words, they completely ionize in water. Some of them, like acetic acid and hydrofluoric acid, on the other hand, they only ionize partially in water. As you can see, ammonia, NH3, is a weak base. Even though it doesn't contain hydroxide ions, it produces hydroxide ions in the reaction with water, as I showed on my introductory video. Now, because we have molarities in these solutions, and the measurement of molarity relates the moles of solute to the liters of solution, we can use it to convert between the amounts of reactants and or products in a chemical reaction. This is the overall conceptual plan or flow chart for these kinds of calculations. So I have one reactant A and I have a volume of it, and because I know its molarity, I can convert that volume into moles. And now I can go to the chemical equation, the balanced equation, and using the stoichiometric coefficients and the stoichiometric ratios, calculate how many moles of B would be equivalent to that number of moles of A. And then, of course, if the reactant B was present also in a solution, I can calculate, well, how many milliliters of that would have needed. So in the case of acid-base reactions, we're going to take advantage of this. And what we're going to do is a technique called a titration. In a titration, you have a substance in a solution of known concentration, and you react it with another substance in solution of unknown concentration. One solution is going to be added slowly from this instrument we call a Buret. It can be spelled with a double T-E or just with just a single T. And you can see it there on the right. It's a long glass tube with markings with a graduated scale. And the solution that we put in that instrument is called the titrant. Just a clarification. The titrant can be either the solution of known concentration or it can be the solution of unknown concentration. It all depends on the experiment that you're doing. So what you're going to have is you're going to be slowly dripping that titrant into a reaction beaker or flask where the other solution is until the reaction is carried to completion. Now, we call that point the equivalence point. And at that equivalence point, we can use the stoichiometric ratios of reactants to calculate the unknown concentration. Now, here's the problem. In acid-base titrations, because both the reactant and product solutions are colorless, a chemical has to be added that changes color when the solution undergoes a change in the level of the acid. And this chemical is called an indicator. We saw one of these indicators. We're going to use it again, and it's called phenolphthalein in part A of this experiment. Now, at the equivalence point of the acid-base titration, the number of moles of hydrogen ions equals the number of moles of hydroxide ions. But we cannot visualize the exact equivalence point. So what we do is we approximate this by observing when the indicator changes color. And that is known as the end point. So in other words, the end point is an approximation of the actual stoichiometric equivalence point. Let's briefly describe where we're going to use the Buret, and then we'll do some demonstrations in a separate video. Okay, the Buret, as you can see, is typically mounted on a special kind of clamp, and the reaction flask is placed underneath it, kind of where the liquid titrant can be delivered without any risk of losing it or dropping it in the wrong place. Notice that because we're going to be looking for a very, very slight, almost imperceptible color change, it helps to put a piece of white paper underneath the reaction flask for visibility of that color change. Notice that because this is a narrow tube, water and aqueous solutions are going to form a meniscus. And so in order to accurately read the Buret, we want to put our eyes and the meniscus at the same level. In other words, place the meniscus at eye level and read the volume as usual at the bottom of the meniscus. Okay, now notice that the Buret is typically calibrated in units of tenths of milliliters, 0.1 milliliter intervals. Therefore, when we record a measurement, we have to add one more decimal. So we're going to record volumes to 2 decimal places. Notice also that in the typical Buret, you are not concerned about how much liquid is in the Buret, but how much is delivered. And for that reason, the scale is kind of reversed from a graduated cylinder. It starts at 0 when the Buret is full, and it moves towards higher and higher numbers, typically up to 50 milliliters, because what you want to read is how much titrant has been delivered, not how much titrant is in the Buret itself. Okay, let's go to our next video, and let's see some of the procedures we're going to carry out here. What we're going to use is, and we're going to come back to this slide later on, we're going to be obtaining a sample of potassium hydrogen phthalate. Notice that we abbreviate it as KHP, but KHP is not a formula. It's not potassium hydrogen phosphorus. No, it's potassium hydrogen phthalate. It's a large molecular weight compound that's very stable. It is a monoprotic acid. In other words, it has a single hydrogen that ionizes. And we're going to show you how to prepare the solution for this acid, which is going to be our standard solution. In other words, this is the one for which we are going to know exactly how many moles of acid we have. So let's go to the next video, and then we'll come back to wrap it up here in the PowerPoint presentation.